Namaste. Welcome back to the session of Basic Thermodynamics. In the previous session, we have gone through few of the problems based on the second law of thermodynamics. So now let us continue with the problems again. Let us go through the problem. A house requires 2 into 10 to the power of 5 kilojoules per hour for heating in winter. In the sense, if a house has to be heated in winter, then it requires 2 into 10 to the power of 5 kilojoules per hour amount of heat. Heat pump is used to absorb heat from the cold air outside in winter. In the sense, the required amount of heat is supplied to the house from the outside environment. In order to do that, they are using heat pump. That too in what season? In winter season. Send heat to the house. This is done by heat pump. Work required to operate the heat pump is 3 into 10 to the power of 4 kilojoules per hour. In order to run the heat pump, the amount of work required is 3 into 10 to the power of 4 kilojoules per hour. Determine first one, heat abstracted from outside, heat absorbed from outside, and the second one is COP, which is nothing but coefficient of performance. Now by looking into the problem, we have to initially decide what kind of machine that they are using. By reading the problem, we have come to know that the machine which has been used is heat pump. Now we have to decide whether it is a machine which is operating directly or it is a machine which is operating indirectly. If it is a direct machine, we will call it as a direct heat engine. If it is an indirect machine, then we will call it as an indirect heat engine. Make sure in case of direct heat engines, the machine is going to give us the work. In case of indirect heat engines, we have to give the work to the machine. Now here the machine has to absorb the heat from outside environment. In order to do so, the machine needs work. We need to supply the work to the machine, which is of 3 into 10 to the power of 4 kilojoules per hour. In the sense, we are supplying the energy to the machine. It falls under indirect category. So here we need to solve the problem by looking on to the directions in which the machine is operating. Make sure work is given to the machine. Now let us concentrate on the data given. Heat required, which is nothing but Q1, 2 into 10 to the power of 5 kilojoules per hour. What do you mean by heat required? This is the demand by the house. That much amount of heat needs to be supplied to the house. I have noted it as Q1. I will come back to that at the later stage. Work required. What is that work required? In order to operate the heat pump, this is the work requirement. So which is nothing but 3 into 10 to the power of 4 kilojoules per hour. Heat absorbed, in the sense, what is the quantity of heat absorbed by the machine from the outside environment, which is Q2 question mark, and COP of that machine, which is nothing but coefficient of performance, is the question mark to us. Now let us understand the given problem through a schematic. Here I have written a schematic. This is the house which is at the top and whose temperature needs to be at higher operating conditions. This is the atmosphere, which is obviously at the cold condition. Now what they are saying us, heat pump is required in order to heat the house. They are heating the house with the help of the heat pump by abstracting the heat from the atmosphere. In the sense, atmosphere is at lower temperature and house should be at higher temperature. In order to do this, heat pump needs a work, which is nothing but work input to the heat pump. So heat absorbed by the heat pump from the atmosphere is notated as Q2. Heat supplied by the heat pump to the house is notated as Q1. Work supplied to operate the heat pump is notated as W. Now we need to understand here T1 is greater and T2 is lesser. That is what the symbols that we are continuously using. So T1 is greater than T2 and heat is supplied from lower temperature region to the higher temperature region by utilizing the external work. I hope we are clear on the notations. Now, by looking onto the sketch, this is the system to us, heat pump. To the heat pump, Q2 is supplied, I mean heat pump is absorbing Q2 amount of heat and W amount of work is supplied to the heat pump. In the sense, two inputs are there and heat pump is giving us only one output, which is nothing but Q1. So now from energy balance, what do you mean by energy balance? What is the number of output that engine is giving us and what is the number of inputs that engine is receiving? Both should be equal to each other. So now input is equal to output. How many inputs are there to the heat pump? Q2 as well as W. Two inputs are there. How many outputs? Only one, which is nothing but Q1. So W plus Q2 inputs will be equal to Q1. Now what are the given data to us? Heat required by the house is given, which is nothing but Q1. Work which is required to operate the heat pump is given. Q1 and W are given to us. Q2 is not given. So solve the equation for Q2. Q2 is equal to Q1 minus W. We have the values with us. Upon operating, we have got Q2 as 1,70,000 kilojoules per hour. That means this is the amount of heat absorbed by the heat pump from the atmosphere per hour. 1,70,000 kilojoules per hour. Per hour, this is the amount of heat that needs to be absorbed by heat pump. The first question is over now. We have answered the first question. Now let us look on to the second question, which is nothing but COP. What do you mean by COP? It is the ability of a device that has been expressed as COP. Here one thing is for sure, if you are operating on direct heat engines, the ability of the machine is expressed with the help of efficiency. If you are operating with the indirect heat engines, then the ability is expressed in terms of COP, which is nothing but coefficient of performance. I have written the coefficient of performance over here. Coefficient of performance is nothing but what is the ability of the machine to the work given to the machine. This is nothing but the input thing. We are giving this input to the machine and this is nothing but a output form. That means machine is giving us. If I want to define the COP of this machine, this is the manual given work and this is the output that we are expecting from the machine. So input is W, output is Q1, which is also a form of output by input only. But we are not going to express it as output by input. Instead of that, ability of the machine to the work input to the machine. What is the ability now? They have mentioned it, 2 into 10 to the power of 5 kilojoules per hour. That I have denoted in the numerator. And work given to the machine is 3 into 10 to the power of 4 kilojoules per hour. Both are in same units, so that I can cancel out each other. I have got COP of the given heat pump as 6.667. That means this is the capacity with which the heat pump is working. Here one aspect should be in our mind. If we are dealing with the engine's efficiency will always be less than 100%. It will come in terms of point decimals. If you are dealing with the indirect heat engines, obviously the COP will be greater than 1 because we are dealing with the indirect heat engines. So now the second question, sub question is also over. We have calculated the heat absorption by the machine and we have also calculated COP, coefficient of performance of the given heat pump. That is what is related to the first problem, and let us move on to the second one now. Let me read the problem to you first. A heat engine, say he is calling it as an engine. Heat engine works on Carnot cycle. The engine is working on Carnot cycle between 900 degree centigrade and 200 degree centigrade. That means higher temperature with which the engine is operating is 900 degree centigrade. Low temperature with which the engine is operating is 200 degree centigrade. If this engine receives heat at the highest temperature, in the sense engine is receiving the heat from higher temperature body. What is the higher temperature value? 900 degree centigrade. At the rate of I mean, what is the quantity of heat that is received by the engine? 50 kilojoules per second. Kilojoules per second can also be expressed as kilowatts. That means this is the amount of heat received by the engine from the highest temperature body, which is nothing but 900 degree centigrade body. Full stop. Calculate the power of the engine. They want us to know what is the amount of work produced by the engine. It is too simple, but we need to look on to the cycle with which the engine is working. Let me write the given data first. Given engine is operating on Carnot cycle, in the sense they have talked about Carnot's engine. Next, T1 is 900 degree centigrade, T2 is 200 degree centigrade. From my notation side, T1 is the highest temperature, T2 is the lowest temperature, and make sure while dealing with the temperatures, we need to deal with absolute temperatures. Absolute temperatures are those Kelvin as well as Rankine. Now they have talked with respect to the ordinary temperatures. Please try to convert these two into absolute. 900 plus 273 will turn out to be 1173 Kelvin. 200 plus 273 will turn out to be 473 Kelvin, capital K. These two are capital K. Right, both the temperatures has been notated with Kelvin. Q1 50 kilojoules per second, which is nothing but in terms of kilowatts, and power is question mark to us. Let us try to understand all these things with the help of the schematic sketch now. I have written source, sink. Source is operating at temperature T1, sink is operating at temperature T2, and I will put a condition wherein T1 is greater than T2. That means source is at a higher temperature than that of the sink. Now T1 is the highest temperature and T2 is the lowest temperature. What is the highest temperature they have given to us? 900, and hence it is T1. What is the lowest temperature that they have given us? 200. So lowest is T2, and hence T2 is 200 degrees centigrade, which is nothing but 473 Kelvin. Now look on to this. This is the heat engine which is receiving Q1 amount of heat from highest temperature source. Highest temperature source is at T1, which is nothing but 900 degrees centigrade. Q1 is the amount of heat absorbed by heat engine. What is that value? 50 kilowatts. They are asking us to calculate what is the power produced by the engine, which is nothing but W. What is this? W. And this is nothing but Q2, heat rejection. Since there is no question on heat rejection, I am least bothered about Q2. So temperatures are given, heat supplied is given, only one question is W, work produced by the machine. Let us look on to the solution now. We know efficiency. Any efficiency can be defined as output by input, which is equal to what is the output from the engine? W. What is the input to the engine? Q1. W by the energy balance, W can be given as Q1 minus Q2. You need to operate energy balance over here. What do you mean by energy balance? Number of inputs is equal to number of outputs. If you do that, W becomes Q1 minus Q2 divided by Q1. Since we are dealing with Carnot engine, what do you mean by Carnot engine? Which is nothing but the reversible heat engine. In case of reversible heat engine, all the temperature ratios can be written as heat ratios. By keeping this in mind, I have written heat ratio as a temperature ratio. Q1 is replaced by T1, Q2 is replaced by T2, and Q1 is replaced by T1. By operating this, 1 minus T2 by T1 becomes the efficiency of Carnot cycle. Now efficiency of Carnot cycle is equal to 1 minus T2, 473 Kelvin, T1, 1173 Kelvin. By operating this, I have got 0.5967, which is nothing but 59.67%. Here that efficiency needs to be understood. What is that value is indicating to us? Efficiency of the machine is 59.67%. In the sense, if you are supplying certain amount of heat to the machine, then the machine is able to convert 59.67% of supplied energy into useful work done. That is what this 59.67 is indicating to us. Then remaining 40, where it is going? 40 or 41, where it is going? it is going as a waste, which is nothing but Q2. That is what is the meaning of efficiency. I hope it is very clear to you. Now again the question is not the efficiency, but the question is work. Again efficiency is output by input, output from the machine is W, input to the machine is Q1. Please cross multiply these two. Q1 times of efficiency will give us the work. So work is equal to efficiency of the Carnot engine times of heat supplied, which is nothing but Q1, which is equal to 0.5967 into 50. This we have obtained from the previous step, and 50 kilowatts has been given to us as the data. Upon multiplication, the work becomes 29.83 kilowatts. This is the work or power produced by the machine, W or P. Now try to understand this. What do you mean by this? W, which is equal to 29.83 kilowatts. What is the amount of energy they have supplied as a Q1, which is nothing but 50 kilowatts. 50 kilowatts of energy is supplied to the machine. Out of that 50 kilowatt, the machine is converting 29.83 kilowatt of energy into useful work. Only that much. How much? 29.83 kilowatt of energy is converted into useful work done. Remaining will be going as a waste, which is nothing but heat rejection, Q2. Since that question is not here, I have not calculated the Q2. Hence, the question power produced by the Carnot machine has been calculated, which is nothing but 29.83 kilowatts. Let me go through the next one. A reversible engine works between. As soon as we look onto the reversible engine, make sure we need to operate with the temperatures. Temperatures of 260 degrees Celsius and 60 degrees Celsius. Obviously, higher temperature will be the source temperature and lower temperature will be the sink temperature. Full stop. Would the efficiency be improved by raising the source temperature by 300 degrees centigrade? The question is, a reversible engine's efficiency can be raised by raising the source temperature by 300 degrees centigrade or lowering the sink temperature by 30 degrees centigrade. Calculate the same. Now it is very clear, we are operating with one of the reversible engine. We can call it as a Carnot engine. For Carnot engines, we don't need the values of heat absorbed, heat rejected or work produced. We need only sink and source temperatures. They have given us the sink and source temperatures. They are asking us the question whether increment in the source temperature or decrement in the sink temperature is going to increase the efficiency or not. This is what is the question. Let us look on to the data. Source temperature is T1 260 degrees Celsius, given data in terms of Kelvin 533 Kelvin. Sink temperature T2 60 degrees Celsius, in terms of Kelvin 333 Kelvin. Now efficiency for these two temperatures, we need to calculate the efficiency initially, because what kind of engine it is? It is a reversible heat engine. I can call it as a Carnot heat engine. That is the first question. Next thing, would the efficiency be improved by raising the source temperature by 300 degrees centigrade? What is the initial temperature that we have? 260 degrees centigrade. By raising this by 300 degrees centigrade, is it possible to raise the efficiency, or by lowering the temperature by 30 degrees Celsius? What was the initial sink temperature? 60 degrees Celsius. By reducing this temperature by 30 degrees centigrade, can the efficiency be improved? These are the two questions that are with us. Let us look on to the solution now. For Carnot engine, we have the equation 1 minus T2 by T1. This we have discussed in the previous problem. Now by looking on to this equation, one thing is for very sure, that if you increase the value of T1 source temperature, obviously efficiency will increase. If you decrease the value of T2 sink temperature, then also efficiency will be increased. That is what he has asked. Rising of the source temperature or lowering of the sink temperature. Which one is the better one? That is the question. So what he has given is correct. Now let us have the maximum efficiency that an engine can have. That too a reversible engine can have. What is that efficiency? Which is nothing but Carnot efficiency, 1 minus T2 by T1, 1 minus 333 T2, 533 T1 in terms of absolute temperature Kelvin. So we have the efficiency of 37.54 percentage. What do you mean by this 37.54 percentage? This is the maximum efficiency that a engine can have. I mean, if it is operating with that temperature limits, this is the efficiency of the engine. Now, rising the temperature is crossing this efficiency, or lowering the temperature crossing this efficiency, that is the question. Which one leads to maximum efficiency? That is the question. Let me take the case 1. In case 1, the source temperature is raised by 300 degrees Celsius. T1 is raised by 300 degrees Celsius, in the sense 260 plus 300, which will be equal to 560 degrees Celsius. In terms of Kelvin, it will be 833 Kelvin. That means now the source, I mean the highest temperature will be 833 Kelvin. By keeping this value, again calculate the value of efficiency. Efficiency will be 1 minus T2 by T1, 1 minus, I have not altered the T2. What was the value of T2 at the initial stage? It is 333 Kelvin divided by T1 has been raised by 300, which is nothing but 833 Kelvin. Upon rising the temperature, efficiency has gone up to an extent of 60.02 percentage. This is the efficiency if you rise the source temperature by 300 degrees Celsius. Next, second thing, if you lower the temperature by 30 degrees centigrade, when T2 is lowered by 30 degrees centigrade, that means you should not alter the original T1 now. What is the original T1? 533 Kelvin. This should not be altered, but you need to alter the T2. That I have done here. T2 initially 60 degrees centigrade minus 30 degrees centigrade. The question would be 333 Kelvin. Now, 1 minus T2 is 303 Kelvin. This I have written over here, divided by T1. What was the original T1? 533, not 833. Make sure original T1 is 533. Upon evaluating this equation, I have got the efficiency as 43.152 percentage. This is also increasing the temperature. What was the original temperature? 37. What is the second case temperature? 43. That is what I have said at the initial stage. In this equation, reducing the T2 or increasing the T1 would rise the temperature. So, increasing the T1 has been raised the temperature, has been raised the efficiency to 60%. Reducing the value of T2 has been raised the temperature to, efficiency to 43%. Now, out of these two, which one is maximum? Rising the temperature of the source by 300 degrees centigrade has increased the temperature to 60%. Hence, we need to choose the first option, which is nothing but efficiency rises to maximum value when source temperature is raised by how many degrees centigrade? 300 degree centigrade. And hence, we need to go through the very first option. That is what is the conclusion for the problem. So, it is very clear, one thing should be in your mind, either reducing the temperature of the sink or by increasing the temperature of the source, efficiency can be improved. Out of those two, which one has to be preferred? That was the question to you. That is what is related to this problem. Let us move on to the next one. A very different kind of problem. An engineer claims to have developed an engine. An engineer has produced an engine. He has claimed an engine producing 4.5 kilowatt of power. Engine is producing 4.5 kilowatts of power. When working between temperatures 1400 degrees centigrade and 350 degrees centigrade. Look on to the temperatures. The machine is operating in between the temperature limits 1400 degrees centigrade and 350 degrees centigrade. In the sense, this is the highest temperature body, this is the source, this is the lowest temperature body, this is the sink, consuming 21,000 kilojoules per hour. Engine receives this much amount of energy. Comment on the engineer's claim. So now, he has produced an engine which is operating between two fixed reservoirs, two fixed temperatures, and it receives a certain amount of energy in the form of heat, and it produces a certain amount of work. Whether the engineer's claim is right or wrong, that is the question. Let us look on to the solution now. Given thing is, the engine is producing 4.5 kilowatt of power. that is nothing but P, which is equal to W. Next, engine is operating between two fixed temperatures, T1 1400 degree centigrade, T2 350 degree centigrade. In terms of Kelvin, 1673 Kelvin and 623 Kelvin. Source temperature, sink temperature. This is the amount of energy absorbed by the engine from highest temperature reservoir, which is nothing but source operating at 1673 Kelvin. The value is 5.83 kilowatt in terms of watts. Now we need to comment on the claim of the engineer. So now let us look on to the maximum efficiency that an engine can have. The maximum efficiency is nothing but the Carnot efficiency, 1 minus T2 by T1, which is equal to 1 minus 623 divided by 1673, which is equal to 0.6276, which is equal to 62.76. Since he has given us the temperature limits will be given only when it will be acting as a reversible heat engine or Carnot's heat engine. So Carnot efficiency for the engineer's claim will be 62.76. In the sense, for that temperature range, the engine will have maximum efficiency of 62.76 percentage. That is what is the engine's maximum efficiency. Beyond that, engine will not go, because Carnot efficiency itself is 62.76. Now let us look on to the engineer's engine's efficiency. Inventor's engine's efficiency will be W by Q1, where W is output, Q1 is input. W in terms of kilowatt 4.5, Q1 in terms of kilowatt 5.83. This 21,000 kilojoules per hour has been converted into kilowatt. The value turns out to be 5.83 kilowatts, which will be equal to 0.77, which is equal to 77%. What do you mean by that? The amount of heat received by the engine, and hence it has got an efficiency of 77%. This efficiency is based on the amount of heat received by the engine, so that this is the actual efficiency that the engine is having. What is that efficiency? 77%. But what is the maximum efficiency that an engine can have? Which is nothing but Carnot's efficiency. What is the Carnot efficiency? 62. What is the efficiency that engine having now? 77. That means the engineer's engine is having more efficiency than that of the Carnot efficiency. That is what I have written over here. Inventor's efficiency will be greater than Carnot efficiency. This kind of situation is not possible in nature. Nature doesn't allow even to achieve Carnot efficiency. Then how can an engine cross the Carnot efficiency? Because of that, whatever the claim that engineer is making is wrong, because always Carnot efficiency will be greater than any other engine's efficiency. So we can conclude that whatever the claim that engineer is going to have will not be claimed, because Carnot efficiency is lesser than that of the inventor's efficiency. So now we have seen different kind of problem wherein we have come to know that Carnot efficiency is the maximum efficiency out of whatever the engines that we are running in nature. Even Carnot efficiency achievement itself is too difficult job. This is what is for the today's session. We will meet in the next session with some more problems. Namaste.